Okay guys, last video we learned about some rotational quantities, and we're going to try to put that information to good use today. This video is ultimately going to be about something called rotational inertia, but I'm going to get to that later. I'm going to introduce it by talking about rotational kinetic energy. So what I've got here is, this is a baton, a long thin rod that's being twirled or spun about its center point. So here is the center point right there, and it's being spun with an omega, and it's counterclockwise or positive omega. And the first thing I'd like to think about is, what would be the kinetic energy of this rod as it's spun? It's a moving mass, so it should have kinetic energy. And we recall from a little while back that the kinetic energy is given by this equation. K equals 1/2 the mass of the object times its velocity squared. So to start off, we might think about how we would apply that equation to the baton. And we might see that we've got to take into consideration that as you move down the baton away from the axis, away from the center, the V's change, right? These V's change. The farther away you are from the center of the baton, the bigger the linear speed is, right? So actually, maybe I'll write that right now just to remember this fact from the last video, that there's a relationship between the linear speed v and the angular speed omega, and we say v equals omega r. So the omega is the same for every point along the baton, but the v's are not, right? The v gets bigger and bigger and bigger as r gets bigger and bigger and bigger. So how would we calculate the rotational kinetic energy? Well, you'd have to imagine maybe cutting this baton up into all of these different bits, all these different pieces. So I'm going to imagine just one little piece right here, and let's call that this little piece right here. That's our little mass element mi. And what you'd have to do then is you'd have to split this baton up into all of these little mass elements, and then take into consideration each mass element and its individual velocity, and you'd have to do a summation. So you'd have to say something like the kinetic energy is equal to the sum of 1/2 mi times the velocity of that mass element, vi squared. So you'd have to do this summation for all of these different little pieces. Since it's a rotational system, maybe it would be nice, or maybe it would be it makes some sense, rather than using v, let's use omega. In other words, I'm going to substitute now in this equation. I'm going to put this whole thing, omega r, in for v. I'm just going to substitute right there. And so what is that going to give us? It's going to give us that the kinetic energy is the sum of 1/2 mi times omega, which is the same, right, for all of it. So I don't have to write it with any sort of subindex, right, because the omega is the same everywhere. So omega squared times ri squared. I've just squared this, omega squared times r squared. I'm just going to rearrange that a little bit, and I'm going to write sum of 1/2 mi times ri squared times omega squared. So I've just rearranged this a little bit. And now I get something that looks kind of like our old kinetic energy equation. The 1/2 is here, right? Here's my 1/2. Same 1/2. And then I've got this thing, right? This thing right here, which looks like my m from up here, right? And then I've got my omega squared, which is similar to the v squared. In other words, this thing, if this is a rotational kinetic energy, this thing looks like the analog for mass right here, 1/2 mv squared, right? This is my rotational, omega is my rotational analog for v, and this thing right here looks like my rotational analog for mass. And indeed it is, we have a name for it. It's called the rotational inertia. So this thing right here, m, I'm actually going to switch colors here. This thing is our analog to mass, and it's called rotational inertia. And it's abbreviated with the letter I. And again, you can think of it as similar to mass. So let's write that equation down here so that we can refer to it. So now we've got rotational inertia, and we know what the equation is. We've sorted that out. So I equals the sum of mi Ri squared. So we'll refer to this equation moving forward. Let's think about, before we even get any further into the math here, how we would use this equation. Let's try to figure out what the equation means, just get some kind of an intuition for what this is all about. When we say rotational inertia, so we know inertia is resistance to acceleration, right? That's our physics definition. So this is somehow related to resistance to acceleration, right? Mass is like inertia, or mass, the word mass sort of refers to this property of inertia, which is resistance to acceleration. And so what this is saying is, if you have something spinning, the amount of inertia, the resistance to acceleration, is related not just to the mass of the thing that's spinning, but also the radius, or the distance away from the center of the axis of rotation, which is an interesting concept. And this isn't maybe obvious, but what this means is the resistance to spinning, if you have an object that's spinning, the resistance to that spinning is related not just to how much mass there is, but the distribution of that mass. To give you a sense, let's imagine you had two spinning objects. So let's imagine a disk. So I've got a spinning disk, and this is going to be a solid disk. So here's a solid disk of mass m. Okay? So it's a solid disk, mass m, and it's spinning, or we're going to spin it, let's say. We're going to try to spin this thing, give it some sort of omega in this direction. And of course, because it has mass m, it's going to have some inertia. It's going to require some effort to get this thing spinning. And then let's imagine we've got a hoop, or or actually I'm going to call it a ring. It's called annular ring is the fancy term for this. So I've got this ring. Try to draw this carefully. Oh, are you kidding me? Go away, Wiley. Sorry about that. So we've got this ring, and the ring is also mass m. So exact same amount of mass. But you can see now that the mass may be the same, but the mass now is not distributed quite the same way. So here's all the mass is in this ring here, right? So the mass is the same amount of mass, but it's distributed differently. In other words, here it's distributed evenly. Here it's distributed in such a way that it's it's on average much farther away on average from the axis of rotation. Meaning, if you were to do this summation, you'd get a larger I. So again, we're going to try to spin this thing, same idea, spin it this way. But if you do this equation, you're going to find this has a smaller I and this has a bigger I, right? This is going to have a larger sum because you're going to take these mass elements m and you're going to be multiplying them on average by bigger values of r. So even though the mass is the same, the inertia, rotational inertia, is not the same. This guy is going to be harder to spin because the mass is concentrated farther away from the axis of rotation. So I hope this example gives you some kind of an intuition as we move forward and get a little bit more technical and talk about the math of this a little bit more, to give you some kind of an intuition for it. I'm trying to think of some practical applications. The one that comes to mind is cyclists pay a lot of attention to the distribution of the mass of the wheel. So if you're a cyclist and you're interested in trying to get that bike to go as quickly as possible, you might pay attention to the moment of inertia of the wheel, and pay attention to the ways in which the mass is distributed in the wheel. And I think there are all sorts of regulations in terms of what exactly the moment of inertia of a wheel can be. But okay, let's get into this a little bit more. And first of all, maybe I'll move down here. If the equation is this, I'll write it again, mi times, sum of mi times ri squared. This is a really easy thing to evaluate if you only have if you have a system of say 2 objects. So maybe I've got, here's m1 and here's m2. And maybe I'm trying to spin these 2 objects about a point. Let's say I'm trying to spin them about this point. Here's my axis. In other words, this then is R1, and this is R2, right? So I could easily just apply the equation right here, and it would be relatively easy. I would say that the I here equals m1 r1 squared plus m2 r2 squared. So that's relatively simple, but if we imagine something like the baton that we were dealing with earlier, we might be able to see that this is going to get a little bit more complicated. So let's think about the baton again. Here's our little baton. And we're going to imagine spinning this baton about the center again. So here's the center, so that's what we're spinning it around. And let's just say that we've got this baton has a mass m and it has a length L. So the length is this whole length from one end to the other. So baton with mass m and length L, and we'd like to know what the rotational inertia is, remembering our definition, sum of mi ri squared. And we can see that we can't just sort of add up all of the little pieces. What are you going to do? You're going to take each individual atom and try to find its mass and its r. That's not the way to do it. So what we'll do is just take an integral. So we'll say, I shouldn't say just take an integral. We'll take the integral. So we're going to say I is the integral of r squared dm. So we're imagining little elements dm. So here's some little element dm right here. And we're going to take r squared dm. Now, how are we going to evaluate this? Well, we're going to evaluate this from the center to dm, right? This is going to be our r is going to be from the center to dm. But so here's r, right? But since there's one half of the baton is to the right of the center and one half is over here to the left of center, if I do this, I'm going to have to end up multiplying the whole thing by 2. In other words, what I'd like to write is this. I'm going to write that the rotational inertia is 2 times r squared dm evaluated from r equals 0 to one end or the other of the baton, which is half L, L over 2. So hopefully that makes sense. I'm imagining taking one half of the baton and I'm evaluating from r equals 0, so this is 0, all the way to down here, which is L over 2, half L, and then I multiply by 2 because there are 2 halves of the baton. Okay, so how would I go about dealing with this thing? Well, I'm going to have to do some sort of a substitution, right? I've got r dm. That doesn't make any sense, but if we accept that this has a uniform density, so the baton has uniform density, and this density, I'm not going to use rho, which we used to use. I'm going to use this figure lambda for this linear density. So it's got uniform linear density, and so that density lambda is equal to m over L, or dm over dl. Now, what I can do is dm over dr, right? This is what we're using as r. In other words, I can rewrite now dm as m over L. Sorry, it's big M over L dr. So I've just rearranged this, solving for dm. dm is m over L dr. And now I can plug this do my substitution, put this whole thing in up here. So this whole argument right here, this whole argument was hinged on the idea that this is a rod or a baton of uniform density, and that density, which I'm abbreviating lambda, is the total mass divided by the whole length, which then we could write dm over dr. And now we've got that substitution. Let's see what our integral looks like now. So now I'm going to write I equals 2 times the integral taken from 0 to L over 2 of this whole thing now, which is going to be r squared times m over L dr. Sorry about that. I'm back. So let's keep working on this integral here. This thing is a constant, right? We have mass m and length L, so we can just now just go ahead and pull that out, and we get now this equals 2 times m over L of the integral of r squared dr. And now we can go ahead and evaluate this thing. So this now is going to equal 2 times m over L of times r cubed over 3 evaluated now from 0 to L over 2. And finish this off now, and we can say that the I, if I continue on here, if I plug in L over 2 in for r cubed, I get I equals 2 times m over L times, what is this thing? I have to take L over 2, right, plug it in for r cubed, so I'm going to get L cubed divided by 3 times 2 cubed. 2 cubed is 8 times 3 is 24. And now this whole thing is going to reduce to 1/12 m L squared, right? So what happened there? I went ahead and I lost an L there, and this turned into 2, and then I took the 2 and the 24, and this became a 12, and so I get 1/12 ml squared. And now this, we can see, is the rotational inertia for a rod. So I for a rod. Now, you can see the logic of how we went about this, the logic in the calculus, but you might be saying to yourself, well, that's great. Now I know how to calculate the rotational inertia for a rod, but there are lots of things out there that might spin that aren't rods, and rings and so forth. So you could go through the same exact logic over and over again for all of the various types of objects that you can think of. Your book does, however, give you a nice handy chart, which I've copied over here somewhere. Here it is. The book does include a nice handy chart for a variety of different shapes. So this is right here, this is the one that we just did. I don't know how well you can see that, but it says 1/12 ml squared, which is a thin rod that's being rotated about an axis through the center, perpendicular to the length, the baton. And you can see a variety of other shapes. So this one we've done, but let's take a look at some of the others. So here is a hoop, and this we're imagining a hoop that has that's essentially, we're ignoring the thickness of the hoop itself. So it's like an infinitely thin hoop or ring. And if it's an infinitely thin, if you don't have to consider the finite thickness of the hoop, then it's just I equals mr squared. Pretty easy. Here's the ring, right, where now we aren't ignoring the width of the ring itself, and so R1 here in this equation is the distance from the axis to the inner edge of the ring, and R2 is the distance from the axis to the outer edge of the ring. So R2 minus R1 would be the thickness of the ring. And then if you do out the integral and make a substitution, you end up with this whole messy thing, which is 1/2 m times R1 squared plus R2 squared. Here's a solid cylinder, or it could be a disc, but they're doing a cylinder that's solid, uniform density. being rotated about a central axis, right? So maybe like you think like a steamroller cylinder. And then if you do at the integral, it's 1/2 mr squared. Here's the same kind of cylinder, but now you can see where the axis is, right? The axis is going through the middle of the thing. Now we get, when you do out the math, you get a slightly different calculation, which is I equals 1/4 mr squared plus 1/12 ml squared. So this is a thick cylinder or disc. You could imagine this being a disc being spun in this way. Here we have a sphere. This is supposed to be a sphere being rotated about an axis. And if you do out the integral, you get 2/5 mr squared. This is a spherical shell, so it's not solid. This is just a shell. And you do it out and you get 2/3 mr squared. So this is 2/3 mr squared, where this one here was 2/5 mr squared. Hoop. The hoop here is the same hoop that we had before, but now we're rotating at about this axis. And we get 1/2 mr squared. And then finally, this one here, this strange one, you have this slab, right? So this, we're imagining a rectangular slab. One side is length A and the other side is length B. And we're rotating the slab, and you get 1/12 m times a squared plus b squared. So a variety, I'm not going to show you, we're not going to do it the integral for each of these different shapes, but in principle for any shape you can go ahead and calculate the rotational inertia I for any shape, and again the book does give you this nice handy cheat sheet, which will be helpful as we do some problems in class. Okay, that's all for now.